66 million years ago, a rock roughly the size of Mount Everest hit what is now the Yucatan Peninsula at about 20 kilometers per second. The immediate blast killed everything within 1,000 kilometers. Vaporized rock ejected into the upper atmosphere circled the planet. Global temperatures dropped, photosynthesis collapsed, and the food chains built on it collapsed shortly after. About 75% of all species on Earth went extinct within a geological eye blink. We call this the End Cretaceous extinction, and its most famous casualties are the non-avian dinosaurs. They had dominated terrestrial ecosystems for 165 million years, nearly 3 times as long as the span of time between their extinction and right now. And in the space of perhaps a few thousand years, they were gone. What if they weren't? That question sounds like the premise of a theme park movie, but it's a legitimate thought experiment in evolutionary biology, and the answers researchers have proposed are more interesting and more uncertain than most people expect. To get there, we need to start with what was actually alive at the end of the Cretaceous, because most people's mental image of dinosaurs is about 80 million years out of date. The dinosaurs of popular imagination, Brachiosaurus, Stegosaurus, Allosaurus, were Jurassic animals. By the end of the Cretaceous, they'd been gone for tens of millions of years. The world 66 million years ago was occupied by a completely different cast. Tyrannosaurus rex, Triceratops, Ankylosaurus, Pachycephalosaurus. Alongside them lived an enormous diversity of smaller theropods, two-legged carnivores with increasingly bird-like anatomies, some feathered, some capable of flight or near flight. The mammals of this period were mostly tiny, shrew-sized, mole-sized, the occasional cat-sized animal. They occupied niches that the dinosaurs hadn't fully colonized: nocturnal activity, burrowing, insectivory, and dense undergrowth. This marginalization is exactly what saved them. Small body size, dietary flexibility, and low caloric needs let mammals survive conditions that killed everything larger. Remove the asteroid. What happens? The most important thing to understand about this scenario is the timescale. 66 million years is an enormous amount of evolutionary time. Modern humans share a common ancestor with chimpanzees roughly 6 to 7 million years ago. The distance between the late Cretaceous and today is enough time for the entire primate lineage, from the earliest primates to every species of monkey, ape, and human that has ever lived, to evolve from scratch several times over. Without the extinction, the dinosaur family tree would have kept branching. Species would have come and gone. The mammals would still exist. They'd been coexisting with dinosaurs for 165 million years already, but they'd have remained in their marginal niches, never producing anything larger than a medium-sized dog. The ecological space that in our timeline opened up after the extinction would instead have been filled and refilled by dinosaurs. The specific species from the Cretaceous would be long gone. Their descendants would be unrecognizable, but the lineages would have continued. The question of whether any of those lineages could have produced intelligence requires asking which dinosaurs were already trending in an interesting cognitive direction. The answer points pretty clearly toward a group called the Truodontids. Truodon formosus was a small theropod from the late Cretaceous, roughly the size of a human, bipedal, with long grasping hands, forward-facing eyes giving it binocular vision, and a brain-to-body ratio larger than almost any other known non-avian dinosaur. It was almost certainly warm-blooded, probably feathered, and showed evidence of behavioral sophistication, including complex nesting behavior. By dinosaur standards, Troodon and its relatives were operating at a noticeably higher cognitive level than contemporaries like T-Rex. The trajectory was there. In 1982, paleontologist Dale Russell collaborated with artist Ron Sagan on a thought experiment that became one of the more famous speculative exercises in paleontology. Russell asked, if troodontid dinosaurs had continued evolving for another 66 million years along the same general trajectory, what might they have become? The result was the Dinosauroid, a bipedal, large-brained, three-fingered creature with a relatively upright posture and a cranial capacity in the range of early hominids. Russell argued that pressures selecting for larger brains in tool-using bipeds would tend to produce certain convergent features regardless of starting point. Forward-facing eyes for depth perception, forelimbs freed from locomotion, reduced jaw structure as diet became less dependent on raw biting force. The Dinosauroid was controversial immediately. The main objection isn't that dinosaurs could have evolved greater intelligence. That seems plausible given the time frame. The objection is that Russell's creature looks suspiciously human. Critics argued this reflects a cognitive bias toward imagining intelligence as necessarily converging on our own body plan. They have a point. A more honest exercise asks what selection pressures would actually drive cognitive evolution in a dinosaurian lineage, and what physical features those pressures would most likely produce. The pressures that drove primate cognitive evolution were social complexity, dietary flexibility requiring problem solving, and tool use. There's no reason to think these pressures are uniquely mammalian. Social behavior was already present in many dinosaur lineages: pack behavior, parental care, complex communication. An environment selecting for better social cognition would work on dinosaurian neural architecture, just as it worked on mammalian neural architecture. The anatomy would probably diverge from Russell's model. Theropod forelimbs were not going to evolve into human-style hands. More likely candidates for manipulative appendages might be highly dexterous feet, Some modern birds manipulate objects with remarkable precision, or a beak-and-claw combination that achieves similar functional outcomes through a completely different route. The brain itself would probably look nothing like ours. Avian brains and birds are living dinosaurs, direct descendants of theropod lineages that survived the extinction process information using a neural architecture fundamentally different from the mammalian neocortex but capable of remarkable sophistication. Crows and ravens demonstrate causal reasoning, future planning, tool manufacture, and theory of mind. A highly encephalized dinosaurian descendant would likely build cognition on that avian-style architecture. What it would be capable of is genuinely hard to predict. Could any of this have led to a technological civilization? Technology requires sufficient intelligence to plan multi-step tool use, enough dexterity to implement it, social structures capable of accumulating and transmitting knowledge across generations, and ecological conditions that permit the food surpluses that free up time for non-subsistence activity. None of these are uniquely mammalian requirements. The dexterity problem is real but probably not insurmountable. Crows manufacture and use tools without anything resembling a primate hand. Octopuses use tools with 8 flexible arms. The specific anatomy matters less than the functional outcome. A sufficiently selected dinosaurian lineage with 66 million years of runway could plausibly get there via multiple anatomical routes. The social transmission of knowledge is already present in birds. Specific foraging techniques and tool use behaviors spread through bird populations via observation and imitation. The infrastructure for cumulative cultural evolution exists in the lineage. Scaling it requires bigger brains, longer lifespans, and social structures that keep generations in contact long enough for transmission to occur. The honest answer to could they have built a civilization is maybe, and probably not for tens of millions of years, and probably nothing that looks like ours. 66 million years is long enough. The theropod cognitive trajectory was real. The convergent pressures for greater intelligence and social, tool-using animals are real. Whether the specific combination of anatomy, ecology, and selective history would have lined up to produce technological civilization is something no one can answer with confidence, because it didn't happen, and the space of possible evolutionary outcomes is enormous. The asteroid that ended the Cretaceous was, from one angle, an arbitrary disaster. From another, it was the specific event that cleared the ecological space that mammals, and eventually primates, and eventually us, needed to exist at all. Remove it, and the most likely outcome isn't a dinosaur civilization. The most likely outcome is a world that keeps doing what the Cretaceous was doing. Large dinosaurs dominating terrestrial ecosystems, mammals in the margins for another stretch of time before the next major disruption reshuffles everything again. But in 66 million years, the improbable becomes possible. The same span of time that turned a small insectivorous mammal into a species capable of asking this question might have turned a crow-smart theropod into something we'd recognize as a peer, or something so alien in its cognition and architecture that we wouldn't know what we were looking at. Intelligence is rare. Technological civilization is rarer. The conditions that produce it are specific, fragile, and probably depend on dozens of factors that look like contingency rather than destiny. We got here. Whether something else could have gotten somewhere comparable, that's a question the fossil record can't fully answer, and might never resolve.